Welcome, travelers, to Adventures in Security. In this video, we explore the history of network protocols from 1974 until today. You can download the video script from the link below. Think of a network protocol as a shared language plus a set of traffic laws. If two computers don't follow the same rules for addressing, timing, error handling, and security, they can't reliably exchange anything meaningful. What's fascinating is that protocols don't evolve just because engineers get bored. They evolve because the world around the network changes. Since 1974, the Internet has gone from a research experiment with a small, trusted community to a global, always-on utility that runs banking, healthcare, entertainment, and critical infrastructure. That growth creates pressure. We need more scale, better reliability, stronger security, and smoother performance on everything from satellites to phones. In this video, we're going to follow a timeline starting in 1974, when the key internetworking ideas that led to TCP/IP were being formalized. Then we'll look at early application protocols like Telnet, great for the era, but insecure by modern standards, and why SSH replaced it. Along the way, we'll connect each protocol shift to the why: scaling problems, congestion, address exhaustion, commercialization, and security threats. By the end, you should be able to look at any modern protocol and say, this is the problem it was designed to solve. Let's start in 1974. At this point, packet switching had proven itself, but there wasn't one network. There were multiple networks, each with its own hardware, addressing, and rules. The big challenge was, how do you make a message travel across different packet switch networks without forcing every network to redesign itself? This is where the classic internetworking idea lands. Build a common glue protocol that can ride over many underlying networks. But that glue has to face reality. Networks drop packets. They deliver packets out of order. They have different maximum packet sizes. Some links are fast, some are slow. So the design problem becomes, what do we standardize end-to-end, and what do we leave to the local network? This framing is the seed of why protocols evolve. As soon as you connect systems at larger scale, you expose mismatches. Early protocol designers had to plan for heterogeneity, different networks, different reliability, and different performance characteristics. And notice, security isn't yet the headline. The early Internet community is relatively small and cooperative, so the urgent why in 1974 is interoperability and resource sharing, not defending against hostile actors. Here's the big conceptual leap. Don't make one gigantic protocol that does everything. Instead, split responsibilities into layers. The Internet Protocol, IP, focuses on addressing and forwarding, getting packets from a source network toward a destination network. IP is best effort. It tries, but it doesn't promise delivery, order, or perfect timing. Then TCP sits above IP and provides what many applications actually need: a reliable, ordered byte stream. TCP handles retransmissions, sequencing, flow control, and later, congestion control. This is huge because it means the underlying networks can be messy and diverse, but applications can still get a clean, predictable communication channel. Layering also creates an innovation platform. Once IP and TCP become common, you can invent new application protocols, email, file transfer, web browsing, without redesigning the whole network. It's like building a universal highway system. Once the highway rules are standardized, lots of different vehicles can use it. And here's a key why. Layering reduces coordination costs. You can upgrade an application protocol without replacing the whole internetwork, and you can add new physical technologies underneath IP without changing every app. That separation of concerns is one reason TCP/IP scales so well historically. Now we jump to a milestone. January 1st, 1983, often described as a Flag Day cutover, when ARPANET completed a coordinated transition from its older host protocol, NCP, to the TCP/IP suite. Why does that matter? Because it signals that TCP/IP isn't just an idea, it's operational reality. Once TCP/IP becomes the common foundation, growth accelerates. Universities, labs, and eventually commercial organizations can join a shared internetwork without negotiating a proprietary vendor stack. Open documentation and community-driven standardization, especially through the RFC process, help TCP/IP spread across different hardware and operating systems. This is another why protocols evolve theme. Once a protocol becomes infrastructure, it attracts new users, and those new users bring new requirements. More sites mean more naming challenges, more routing complexity, more performance problems, and eventually more security threats. The Internet is leaving the small club phase and starting to become a general-purpose communication system. That shift drives everything we'll discuss next: DNS, BGP, congestion control, addressing fixes, and the move from Telnet to SSH. With TCP/IP providing a stable foundation, developers start building the everyday tools of the early Internet. Telnet gives you remote terminal access. Basically, you type on your keyboard, and it's as if you're sitting at a distant machine. FTP handles file transfer, and SMTP becomes the workhorse for sending email reliably over TCP connections. These protocols are perfect examples of designs that fit their era. In the early Internet, the environment is more trusted. The main problems are functionality and interoperability. Can I log into that machine? Can I move this file? Can I send a message? Encryption and strong identity verification are not the defaults because the threat model is different and compute resources are limited. But here's the catch: protocols bake in assumptions. Telnet, for instance, is very good at being a general, byte-oriented remote terminal protocol, but it doesn't assume an attacker is listening. As the network grows and becomes commercially valuable, those assumptions stop being safe. So when we later talk about SSH replacing Telnet, it's not because Telnet was bad engineering. It's because the Internet became a very different place, and the why changed from connectivity to connectivity, plus security. As the Internet community expands, you hit a scaling wall, naming and routing. Early on, you could imagine a central list mapping names to addresses. But as hosts multiply, that approach becomes brittle and expensive. DNS, the domain name system, solves this by distributing the database and delegating authority. Instead of one master list, you get a hierarchical system where different organizations can manage their own zones, and caching reduces load. Routing has a similar story. Inside a small network, routing is mostly a technical problem. Find a path. On the global Internet, routing is also a policy problem. Organizations want control over where traffic enters and exits, how they buy transit, and what they advertise. That's why BGP matters. BGP is the protocol that lets autonomous systems, think ISPs, large enterprises, big cloud networks, exchange reachability information while supporting policy decisions. So the why here is growth plus boundaries. The Internet isn't one organization, it's a federation. Protocols had to evolve from one community, one admin, to many communities with their own rules. DNS and BGP are foundational responses to that reality. Now let's talk about a less obvious evolution. Not new protocols, but major improvements to TCP behavior. In the 1980s, the growing Internet experienced episodes of severe congestion, too much traffic, too many retransmissions, and suddenly performance falls off a cliff. This is sometimes described as congestion collapse. The network carries lots of packets, but not much useful work gets delivered. TCP originally focused on reliability. Retransmit if needed. Keep the pipeline full, but in a congested network, that instinct can backfire. Retransmissions add load right when the network is already overwhelmed. So TCP evolves congestion control mechanisms, such as slow start and congestion avoidance. The basic idea is probe the network carefully, increase sending rate when things look healthy, and back off quickly when congestion is detected. The why is simple. The internet had to become stable under load. It's not enough to connect networks. The system has to remain usable when millions of independent senders share common bottlenecks. Congestion control is an example of protocol evolution driven by emergent behavior, problems you don't see until the system grows large enough. As more organizations connect, IPv4 addressing runs into two linked problems. We're running out of addresses, and routing tables are growing too fast. Early IPv4 used classful address blocks that wasted space and encouraged lots of separate route announcements. CIDR, classless interdomain routing, improves this by allowing flexible prefix lengths and, importantly, route aggregation. If a provider allocates addresses in a topologically sensible way, it can advertise one aggregated route instead of thousands of tiny ones. Inside organizations, another strategy appears: private address space. RFC 1918 reserves blocks, like 10.0.0.0/8 for internal use. That lets companies build big internal networks without consuming globally unique addresses for every device. Then NAT, network address translation, becomes widespread, allowing many private hosts to share a smaller number of public addresses. NAT buys time, but it adds complexity and can interfere with end-to-end connectivity. The long-term architectural answer is IPv6, which expands addressing dramatically and supports modern features like simpler auto-configuration. The why across all of these changes is growth. More devices, more networks, and more pressure to keep global routing scalable. Here's the turning point in the story. The threat model flips. Once the internet becomes a global, commercial, always connected system, you have to assume someone might be listening, tampering, or impersonating. Protocols that were fine in a trusted research environment become risky. Telnet is a perfect teaching example. It's great at remote terminal access, but classic Telnet traffic is plain text, meaning usernames, commands, and even passwords can be captured by anyone who can sniff the network. You can try to patch around that with add-ons, but in practice the world moved toward a better default. Make the secure version the normal version. So when we ask, why did SSH replace Telnet? The answer is, because the internet stopped being a friendly hallway conversation and became more like a crowded city street. If you wouldn't shout your password across a crowded room, you shouldn't send it unencrypted across a shared network. Security stopped being optional, and protocol evolution followed. SSH, Secure Shell, was designed to solve the remote login problem correctly for an untrusted network. In plain terms, SSH wraps your entire session in cryptography. That gives you confidentiality. Eavesdroppers can't read your traffic. And integrity. Attackers can't silently modify commands or results without being detected. SSH also tackles a subtle but critical issue: server authenticity. It's not enough to encrypt. You also want to know you're logging into the right machine and not a lookalike attacker. SSH supports server authentication and commonly uses public key cryptography, so you can manage access without sending reusable passwords over the wire. In practice, SSH becomes the standard replacement for Telnet in system administration and networking gear management, and it grows beyond remote login. SSH can tunnel other traffic, forward ports, and support file transfer workflows. So the why here is straightforward. As soon as sniffing and impersonation become realistic threats, secure by default protocols win. SSH is protocol evolution, driven by the Internet's shift from a trusted academic network to a high-stakes global infrastructure. When the web takes off, HTTP becomes the common application language for content and APIs. But early web traffic is also plain text, which creates obvious risks: interception, modification, and impersonation. That's where TLS, Transport Layer Security, comes in. TLS creates a secure channel that can sit under application protocols, most famously HTTPS for web browsing. What changes over time is not just whether encryption exists, but how default and how efficient it becomes. Modern TLS versions are designed to be faster to set up and harder to misuse. TLS 1.3, for example, modernizes the handshake and removes older, weaker cryptographic options. The why here is the Internet's changing role. Once people are shopping, banking, learning, and working online, confidentiality and authenticity become table stakes. At the same time, performance matters because users abandon slow experiences. So, protocol evolution in the web era is about doing security at Internet scale, secure by default, without making everything painfully slow. To close, let's look at what evolution means today. The Internet has tons of middle boxes, NATs, firewalls, load balancers, that sometimes assume old behaviors and accidentally block new ones. That can make it hard to deploy new transport ideas directly on top of TCP. QUIC is a modern response. It provides a secure transport with features like multiplex streams and low-latency connection establishment, but it runs over UDP, so it can be updated more quickly in user space. It's also designed to handle mobility better. Think of a phone switching from Wi-Fi to cellular because it supports connection migration across network paths. HTTP/3 builds on QUIC to improve web performance, especially by reducing certain head-of-line blocking issues and speeding up handshakes in many situations. So the why for modern protocol evolution is a blend of factors. We want lower latency, better behavior on lossy wireless links, encryption by default, and a deployment story that works in the messy real world of today's Internet. The overall lesson from 1974 to now is consistent. Protocols evolve when the environment changes. Scale, economics, performance expectations, and security threats reshape what good networking requires. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.